Okay, so we're going to start a little early on this one and probably end early because this one's short. I don't know what happens in here sometimes. All right, so ways of expressing concentration. And the sign-in sheet is coming around, is that right? Okay, yeah. So this is going to be really fast because I'm going to basically go through most of these slides and tell you that you don't need to know it. Okay, those people who want extra credit need to stop crawling on the floor. That's just one of my policies that I don't usually talk about because it doesn't usually come up, but there it is. All right. Yeah, for future reference. All right. So ways of expressing concentrations of solutions. Like I said, I'm going to skip over most of these slides because the AP exam says you don't really need to know them. So I might talk about them briefly. Mass percentage, you take the mass divided by the total mass. That's easy, right? We've done several of those types of things. So, but they specifically said in terms of concentration, you don't need to know how to do that. Parts per million, parts per billion, that could come up sometimes when we're talking about toxic substances where just a tiny, tiny amount of it could actually be detrimental to living things. So parts per million, you take the mass of whatever it is in the solution divided by the total mass and multiply it by a million, okay? Because it's going to be such a small percentage otherwise that just doing a percentage would be kind of awkward because it's going to be such a small number. But again, you don't need to know how to calculate that for the AP exam. It's not on your equation sheet, and they specifically said in an exclusion statement, students don't need to know how to do this, okay? Parts per billion, same thing except you multiply it by a billion instead of a million. So we can skip the sample problem that has to do with that stuff because we're not doing it. Mole fraction you do need to know, okay? But really the mole fraction thing is more in the context of gases, the partial pressures we talked about in the last unit. So you already basically know how to do that one. Take the moles of whatever it is divided by the total number of moles. So you can do that for a solution as well as for gases. And technically, most mixtures of gases are considered solutions because they're homogeneous mixtures. Sometimes you might need the mole fraction of solvent, not solute. Now that's really more if we're talking about colligative properties. So again, you don't really have to pay attention to that. Molarity, you do need to know. But you already do, right? Moles over liters, we've been doing that all year. Excuse me. So that's not difficult at all. I'm going to give you some more practice problems on molarity. Something in my throat. I'm going to give you more practice problems on molarity, or actually I just did today. But they're not going to give you any difficulty, I don't think. One thing that you might need to know is, that we haven't talked about before, molarity is temperature dependent. Because if you heat something up, its volume changes a little bit. Now, for a solution, that's really not a major change. Okay, but it can change a little bit, so that makes molarity technically temperature dependent. So the concentration of a solution could change if you raise the temperature or lower the temperature. And that's why molality is sometimes used, because it doesn't have that issue, because kilograms is going to be the same no matter what. But again, they specifically said you don't need to know molality for the AP exam, all right? So basically, why are we even covering these sections? I don't know. So again, this is not, molality is not temperature dependent, but I don't think you would need to know that. You would just need to know that molarity is. This is a molality problem, so we don't need to talk about that. Changing molarity to molality, you don't need to know how to do that. Mole fraction, that's percent by mass, so you're not going to need to know how to do that either. Molality, nope. Okay, here we go. This is one that you might need to know how to do, something along these lines. So 5 grams of toluene, 225 grams of benzene, and it has a density of 0.876 grams per milliliter. We want to know the molarity of that solution, okay? So our strategy here would be to probably figure out the number of moles that we have, right? And then we need to figure out the number of liters that we have. So how do we figure out, well, first of all, what's the solute, what's the solvent?
A spectroscope, tube, pliers in the back.
Okay, so what's the solute and what's the solvent here? Okay, benzene is the solute, right? Okay. Now, wait. Solvent. I was just going with what you guys said, and you said the wrong thing. How'd you do that? So this, remember, the way that we can tell this is because of the one that there's less of, right? Okay? So there's only 5 grams of toluene, so we're going to call that the solute. Okay? Now, you have to remember with molarity, the actual formula here is moles of solute divided by liters of solution. Okay? So that's a little tricky. We'll come back to that in a second. But the first thing we have to figure out is how many moles of solute do we have. So we need to change the 5 grams into moles, right? 5 grams of the C7H8 into moles of C7H8. That's going to be, I'm going to approximate here for the sake of time.
Oh my gosh, that looks hard.
So 5 divided by 92. That's not right. So 0.05, what are we doing sig wise here? 0.054 moles. Okay, so that's the C7H8. Now, how do we find the liters of solution here? Okay, we need to add the solute and the solvent together. That's going to be the total mass of the solution, and then what? Use the density, right? Okay, so we've got the 230 grams of the entire solution, okay? And then if you do this using dimensional analysis, grams on the bottom, milliliters on the top, and the density is 0.876 grams in 1 milliliter, okay? So that's going to give us 263 liters of solution, okay? No, that's milliliters, sorry. 0.263 liters. I'll just do a shortcut there because you got to eventually change it to liters. If I'd planned this a little bit better, this would have been right underneath this one, and then I could have just put a divide sign there. Oh well. So then the molarity is going to be calculated like that, okay? 0.054 divided by the 0.263, and that gives me 0.2, I guess 0.21. Did I do that right with my sig figs on the... Yeah, because that's only 2 sig figs, so 0.21. And you can either write the big M for molarity, or you can write moles over liters. Either one is fine for the unit. It's not too bad, right? We've basically done problems similar to that before, so. Okay, so colligative properties. Forget about it, because we don't have to talk about colligative properties this year. And there's a lot on colligative properties, so we get to skip all of this. Which some of it's actually kind of cool, but we just don't have time. All right, so the last thing we do need to talk about, and this will be very brief, is colloids. All right, and I don't know that we talked about colloids last year, did we? Okay, basically a colloid is, well, I wasn't talking about in AP Chem, I was talking about in honors, but I don't think we talked about it in AP Chem last year either. They just briefly mention it in the AP curriculum, so I'm just covering my bases here, but I don't think I need to go into as much detail as I am, probably. It would just be good if you know what colloids are, okay? So basically, colloids, it's going to be, they're larger than individual ions or molecules, too small to be settled out by gravity, okay? So they're not going to sink to the bottom of the solution, but they're larger than just individual ions or molecules too. So in other words, their particle size is kind of in between a homogeneous mixture and a heterogeneous mixture. Okay? In a heterogeneous mixture, they settle out so you can see the parts. In a solution, a homogeneous mixture, the particles are so small they don't even disperse light when you shine light through it. Okay? But the colloid particles are just big enough that they will scatter light when you shine light through it. Okay? But they're not so big that they sink to the bottom. So they're right in between homogeneous and heterogeneous on the continuum. Like, I don't remember which one you're talking about. Which lab? Oh, yesterday. No. So in that one, in what? Yeah, was it number 5? Number 3? Yeah, it would have been maybe either number 3 or number 5, because those are the two that might not have dissolved very well. But with the lab yesterday, what was going on there was it was just slightly soluble. So the stuff that did dissolve would have been forming a homogeneous solution. The stuff that didn't dissolve would be heterogeneous. So if you just put in just enough of it that it could all dissolve, it would form a homogeneous solution, if that makes sense. Okay, so this is a little different. This is examples of colloids where you're talking about like fog, smoke, whipped cream, milk. The proteins in the milk actually form a colloid. Paint is a colloid. I didn't know marshmallows were a colloid. That's funny. Butter. So all of these things have these larger molecules in them. Okay, so they're large enough that it's not just a homogeneous solution. Okay, but they're not so big that we would call them heterogeneous either. They just kind of fall right in that in-between range. Okay. They are usually dispersed evenly, yeah. So colloidal suspensions scatter rays of light. So I don't know if you can tell this or not. This solution on the right, not really scattering light. You can't see the light going through it, okay? But the one on the left, you can actually see the beam of light there, okay? If you can see the beam of light, that means it's being scattered by the particles that are in it, so that would be a colloid, okay? Another example of a colloid would be fog, okay, or really water in the atmosphere can help to kind of scatter the light, and so that's why you get sunsets that turn red. Or, you know, fog coming through, or light shining through fog in a forest, or that sort of thing, okay? So those are all examples of colloidal suspensions. Now, this can be important in biological systems as well. So those of you who have taken advanced biology classes at this point, you've got hydrophilic, hydrophobic. Basically, hydrophilic means it's attracted to water, okay? And hydrophobic means it's repelled by water, it's not attracted to water, okay? So things that are polar, they're going to be hydrophilic, they're attracted to the water. Things that are nonpolar are going to be hydrophobic, okay? And so basically, if you've got something like sodium stearate, I guess is how you say that, it has a polar end and then a nonpolar end, right? And so the advantage to having something like that is that they can actually help with emulsification, okay? And emulsification basically means if you've got these fats in the blood, now they talk about this in the book in terms of digestion, okay? So in order for your body to be able to digest your fats, it needs to keep the fat molecules separate from one another. If they start to clump together, then the body can't really digest them well. So what happens is you've got this stearate ion. Okay, now they're showing it in terms of an oil droplet. This can happen in terms of fats as well. Okay, but these stearate ions, they're attracted. Their non-polar end, is attracted to the oil. Okay, their polar end is attracted to the water, and so they can end up being sort of a go-between. And what they do is they form a little bit of a charge on the outside of the oil droplet that would keep one oil droplet from combining with another oil droplet when in the water. So it basically keeps the droplets separate from one another so that they can be dispersed evenly throughout, okay? If that doesn't happen, then something called coagulation occurs. Coagulation is when those droplets start to come together and they clump and then they form a big mass, and then they will eventually they'll fall out of the solution at that point. They wouldn't be a colloid anymore. Okay?
Jeremiah Jackson,
So
Travis Hart, comes to
that's
main
kind of the
office, please.
significance
Thank you.
of some of those things that have, polar heads, non-polar tails, that sort of thing. Okay? Another example of that is the cell membrane, right? The lipids in the cell membrane have a polar head and a non-polar tail. And I think that's pretty much all I need to say about colloids. There's some stuff in the book that you might want to look over, and I pointed out in the reading guide. That's kind of cool as far as biological systems, but other than that, there's not a lot to it. So there you go. We'll see you tomorrow, I'm pretty sure. Yeah, why isn't there applause at the end of these videos? Exactly.
There is now.